In order to achieve the cognition aspect of the cognitive digital twin, we employ semantic knowledge graph technologies as the method for knowledge representation and integrating data from different sources such as digital twins and hybrid digital twin. Accordingly, SINDIT, SINTIF Digital Twin Framework, a knowledge graph-based digital twin framework, was employed to develop the cognitive digital twin in this Sidenor pilot. SINDIT is an open-source framework that is available in our GitHub repository. SINDIT is also added to the COGNITWIN toolbox under the Digital Twin Representation Tools and Services category. This is the data pipeline that we employed to generate the knowledge graph and to integrate domain expert knowledge into the knowledge graph. First, we use RML, the rule mapping language, to define the mappings from structural data generated by the digital twins and hybrid digital twins to RDF triples. Then we use Morph-KGC, a knowledge graph construction engine, to execute the mappings and build the graph. Once the graph is generated, the domain expert knowledge will be integrated under the form of reasoning rules. A reasoning engine will execute those rules on the knowledge graph to assist the operation in making decisions for production. This is the information model created based on the data from Sidenor pilot. The main asset here is the ladles, which can be used multiple times in various heats. During the heat run, the alloys can be added multiple times. There are also cyclic data such as sample temperature, process parameters which are stored in a timeseries database. The outputs from hybrid digital twins, such as prediction models, are also integrated. We used this information model to create the ontology for the knowledge graph. This is the dashboard of SINDIT. Here we have multiple ladle nodes. When clicked, the properties of the node will be shown in a separate window on the right. You can also filter only interested nodes by using the toolbox on the left. Here we select only ladle 1. You can expand the node with other nodes connecting to it. Here, we have multiple ladle use nodes for ladle 1. Each ladle use is associated with one heat node. The heat node has multiple alloy addition nodes. Each heat node has one prediction node, which contains the outputs of the hybrid twins as well as the reasoning results. The domain expert knowledge represents the instructions and experiments of the human operator regarding making maintenance decisions for the ladles. For example, the ladles may be repaired if they have been used in more than 33 heats or demolished after 69 heats. Also, if the thickness of the brick lines is less than 50 mm, the ladles must be repaired or demolished. These are the reasoning rules developed based on the domain knowledge. For example, we have rules to recommend the operator to analyze the ladles if the heat use range is from 33 to 46 or from 69 to 85. Other rules also check the thickness of the brick lines, larger than 70 mm, between 50 and 70 mm, or less than 50 mm, and recommend actions accordingly. The reasoning results are added to the prediction node of the heat and can be used by the human operator to make maintenance decisions for the ladle after each heat run. For example, here, there is no action needed because the ladle has been used in only 4 heats, and the thickness of brick lines is still in operation range.